I'm Nicole Ma, a senior at CESASC School with a passion for unraveling the mysteries of our changing climate. My journey into the realm of earth science and global warming began as an intern at Caltech, where I worked with Dr. Jonathan to dive into the intricate web of regional and global surface temperature warming. My focus has been on understanding the acceleration of these warming trends and pinpointing the timing of crucial tipping points that lie ahead for various regions. Through rigorous analysis and data-driven insights, I've contributed to the body of knowledge surrounding climate change, providing estimates on when these pivotal moments might occur. By painting a clearer picture of what's at stake, my research lays the groundwork for crafting strategies that can mitigate the pressing climate challenges we face. In recognition of my contributions, I was honored to receive the CESASC JHJ Prize in Physics, and I'm excited to share my research and insights on how to mitigate global warming at CESASC's New Era Talk. I'm also the president of the AEC Foundation's Eco-Justice Global Alliance Club, where I've partnered with the United Nations to lead a team to develop books and use activism to address climate and environmental injustices around the world. In my free time, I love watching Formula 1 and Formula E, as well as reading philosophy books. Thank you so much, and I hope to see you all at the New Era Talk. Hi, I'm Nicole Ma, a senior at CESASC School with a passion for unraveling the mysteries of our changing climate. My journey into the realm of earth science and global warming began as an intern at Caltech, where I worked with Dr. Jonathan to dive into the intricate web of regional and global surface temperature warming. My focus has been on understanding the acceleration of these warming trends and pinpointing the timing of crucial tipping points that lie ahead for various regions. Through rigorous analysis and data-driven insights, I've contributed to the body of knowledge surrounding climate change, providing estimates on when these pivotal moments might occur. By painting a clearer picture of what's at stake, my research lays the groundwork for crafting strategies that can mitigate the pressing climate challenges we face. In recognition of my contributions, I was honored to receive the CESASC JHJ Prize in Physics, and I'm excited to share my research and insights on how to mitigate global warming at CESASC's New Era Talk. I'm also the president of the AEC Foundation's Eco-Justice Global Alliance Club, where I've partnered with the United Nations to lead a team to develop books and use activism to address climate and environmental injustices around the world. In my free time, I love watching Formula 1 and Formula E, as well as reading philosophy books. Thank you so much, and I hope to see you all at the New Era Talk.
Okay, right now it's 6 o'clock. Let's give another minute or two, and some people still logging on. Okay, thank you. Yeah. Okay, let's go ahead to start it. And today we have a speaker to talk about the climate change. And many people was wondering, what is the climate change? And many people even know, climate change sometimes is debatable because, people sometimes use this climate change rather than the scientific facts, but they are using it as a political purposes. So, and when I was at Nicole's age, okay, when I was a teenager, I remember at that time, and so my school teacher, showed me a chart of the CO2 levels and in Hawaii and so on. On that chart, I remember the CO2, which is carbon dioxide in the atmosphere, is around 310 or 320. I can clearly remember. Now the CO2 levels, if you go to the website, okay, climate.nasa.gov, you'll find, hey, the CO2 level is over 420 already. Okay, you go to Google, go to the Google search, you ask the following questions, you type in the Google search, when CO2 level is going to reach 500, Google will tell you by 2050, okay, which is less than 30 years from now, it's going to reach 550 parts per million values for the CO2. Okay. By 2026, actually, it's next year, it's going to overshoot the 450. Okay. Now, how about by 2100? The CO2 level by 2100 is going to be at least 950, maybe 1,000. So what is the consequence of that? What is the future weather is going to look like? Okay, the future's weather, it means the climate. Okay, so to answer these questions, there's no magic. You have to base on the physics. You have to ask the climate modelers to do that. The climate models is developed by the best mind on the earth. Different countries have different climate models. You can ask US, what is the best climate models in the US? What is the best climate model in Europe? For example, what's best climate models in China? For example, those climate models are developed by scientists, smart scientists. Of course, the climate model has uncertainties. Okay. Some of the model says, hey, and so the CO2 level is going to be this much, and global warming is going to this much, plus minus a large error bars. And different climate model may have different error bars. That's uncertainty. But this is the best tool we have. Okay. So I have a student here, and who is 16 years old. Okay, at Sage High and school. Okay, Sage Hill High School, and she helped me over the past summer to conduct some of the research because we want to figure out when the climate model is going to predict by how much the global warming is. Okay, so she select the best climate models we can find, how to select best climate model to see which climate model, when they do the historical simulations, match best with the observations. Okay, and so the observation is not a global mean, it's on different regions. What is the observation in tropics? What is the observation in the mid-latitude and high latitude, both north and south? Then she picked the best climate models, matched with the observation, which is more than 10, to do the predictions into the future. Okay. At the same time, when Nicole was doing this research, there's another group of scientists, they published a paper, say, if the global warming is over 1.5 degrees Celsius, we are going to go into a regime. And so we're going to hit the tipping point. The people is asking, what is the tipping point? Okay, tipping point actually is a state. If you cross over the state, the climate system is going to go into another equilibrium. What is the equilibrium? Equilibrium is the forcing and feedbacks balanced state. We are currently in one of the equilibriums, okay, which is our climate. Now, many years ago, the Earth used to be in the ice age, which is different equilibrium climate, okay, different climate. Now, if the CO2, the greenhouse level is going to increase, we are going to shift into another state, which is much warmer, another equilibrium. Okay. Now we are very close to that equilibrium, and we are very close to the tipping point to slip into another equilibrium. How do you know that? You see, very frequently, and so there's extreme weathers, there's heat waves, for example. What is the heat wave and extreme weathers? Those are the flickerings of another state skip into our state, another equilibrium, okay, skip into our state. Now, when the time passes by, if you're very close to the boundaries of that equilibrium, you'll see more frequent heat waves. Okay, now the heat wave maybe once a month. Later will be more frequent. Why? Because we are very close. So that's the tipping point. Nicole is going to tell you more about this. Okay, when we are going to reach the tipping point, and that's the research, and Nicole is trying to answer. Okay, so without further ado, and I'm going to ask Nicole and to open the very good and open the video. You can share the slides to start your presentation. Okay, thank you very much. Okay, go ahead, Nicole.
Okay. Hi everyone, my name is Nicole Ma, and today I want to talk to you about global warming and tipping points, which I believe are the greatest existential threats that humanity has faced. So, as we've seen in recent years, the impacts of global warming are escalating at an alarming rate. Catastrophic heat waves, floods, wildfires, and other extreme weather events are devastating communities around the globe. And the data clearly shows that greenhouse gas emissions from human activities are driving rapid changes to the climate system that threaten life as we know it. For example, as we all know, Hurricane Hilary recently formed as a powerful Category 4 storm over the warm Pacific waters, before weakening to a tropical storm that brought severe flooding to areas of California. Numerous studies have linked global warming to more intense hurricanes, rapid intensification, precipitation rates, and death tolls from storms, especially the most intense Category 4 and 5 hurricanes. One study found that since 1975, there has been a substantial and observational regional and global increase in the proportion of Category 4 to 5 hurricanes of 25 to 30% per degree Celsius of anthropogenic global warming. Beyond hurricanes, other extreme weather events are clearly linked to global warming. Heat waves are longer, hotter, and they occur more often. In 2022, at least 90 people were killed in India and Pakistan alone due to a heat wave in late March that soon led to one of the hottest March-April periods in South Asian history. And temperatures in Pakistan even reached up to a scorching 49.5 degrees Celsius in May. A record 47 degrees Celsius daily high was recorded in Portugal, and heat-induced complications greatly contributed to the 53,000 excess deaths across the European continent in July. Wildfires are also more severe and burn more acreage as hot, dry conditions persist. And droughts are also intensifying in certain regions. Climate change acts as sort of a threat multiplier, significantly increasing hazards posed by extreme weather and undermining resilience. We are already witnessing the costly consequences in lives lost, damage to homes, infrastructure, and crops, and communities being displaced. And make no mistake, even more dangerous long-term warming consequences loom if climate change continues to be unchecked. Sea level rise will redraw coastlines and sink entire island nations. Food systems will be undermined. Ecosystems will unravel to mass extinctions. Human health and livability will degrade. These extreme weather events offer a warning and glimpse of our future if we do not urgently cut emissions and draw down carbon pollution. But we must also remember that climate change is not just about short-term disasters. The escalating and profound long-term threats to civilization and nature ultimately pose as the greatest existential risk humanity has faced. So in 2022, a climate scientist named James Hansen published a paper reaffirming the existence and the prevalence of global warming acceleration in the past decade, using the deviation of global temperature anomalies in recent years from the linear warming rate of 1970 to 2020. His study attributes this acceleration to the energy imbalance of our planet and an increasing intent in net climate forcing. So I also performed some analysis on the rate of global warming. First, I performed a polynomial fit on historical surface temperatures gathered from observational datasets in the years 1880 to 2020. So by taking the first derivative of this curve, we obtained the rate of global warming. As you can see, the rate is consistently positive, meaning temperatures have been increasing over the years. Moreover, the rate itself has been increasing. And this is more prevalent when you take the second derivative and you obtain the acceleration. All the points on this line are positive, which suggests that not only is global warming accelerating, but the rate of that acceleration itself has been increasing with time. This confirmation that global warming is accelerating pushes forward the question, what will the future of surface temperatures and thus the future of our Earth look like? First of all, as global warming continues to accelerate, tipping points begin to approach. A tipping point is a critical threshold in the climate system that leads to large, often irreversible changes when crossed. In our climate system, the crossing of a tipping point is likely at 1.5 degrees Celsius of warming above pre-industrial levels, and highly probable at 2 degrees Celsius globally. As of right now, we have already reached 1.1 degrees Celsius of warming. This is extremely significant because the breaching of these tipping points will lead to changes in all facets of life, ranging anywhere from a dramatic loss in biodiversity to compounding the issue of food insecurity that's already so prevalent in society today, to increased amounts of deadly natural disasters. Our civilization is fragile. Our entire population depends on agriculture and abundant sources of drinkable, clean water. Our species has actually been enjoying an exceptionally quiet period for the past 12,000 years, which is when we first started settling down and started farming. Tipping points will completely destroy these millenniums of quiet. As Dr. Jonathan explained before, we haven't quite crossed the edge yet, but we're dangerously close. The extreme weather events that I described before are an early warming sign, a flicker of what lies on the other side of a tipping point. An important thing to note is that different latitudinal regions of the world are warming at significantly different rates from each other and will reach different degrees of warming at different times. So not only is it important to look at global surface temperature projections, but it's also important to look into regional ones and find out what the future of surface temperatures will look like both globally and regionally, which was the main objective of my research as a Caltech intern. So the first stage of my research was observational analysis. Specifically, I looked at 2 datasets of surface temperature anomalies, both globally and in 3 different regions, the Arctic Circle, the Antarctic Circle, and the tropics. So these figures here graphically illustrate the differences in warming rates in 3 different regions in comparison to global surface temperature anomaly trends. For my research, I looked at 2 sets of historical observational data, one from NASA GISTEMP, which is the graph on the left here, and another from Berkeley Earth. And the data from these 2 sources were manipulated using X-ray and climate data operators. So the first region that I looked at is the Arctic Circle. The Arctic is warming at a much faster rate than the planet, at more than 2 times the rate, which can easily be observed by the slopes of the linear trends. Elevated warming rates in the Arctic can be attributed to the Arctic amplification phenomena, which has a plethora of factors behind it. One of them is the ice albedo feedback loop, which is when melting sea ice exposes more dark ocean with lower albedo, which then absorbs more heat and causes more ice to melt, and the cycle continues from there. The significant warming rate and acceleration in the Arctic is a significant deal because it has a lot of consequences that are completely reshaping the essence of the Arctic, affecting both humans and wildlife. For example, just between 1998 and 2016, the overall number of caribou and reindeer in the Arctic declined by 56%, and the majority of this decline can be attributed to the reshaping of Arctic land due to global warming. The graph on the left here shows the surface temperature anomalies of both the planet overall and the Arctic, as well as the 60-month moving averages and their linear trend lines. And it's easy to see how extremely surface temperatures in the Arctic are accelerating. So next is the tropical region, which is warming slightly slower than the planet. This slower warming rate can be explained by tropical tropospheric temperature variations that cause radiative resistance to temperature change or increase. So as in the previous graph, this one compares the tropics to the global surface temperature trends. As you can see, the surface temperature curves in the tropic have much closer trends in temperatures to the global ones when compared to the Arctic. Finally, the Antarctic region, which is also warming slightly slower than the planet. This also has a variety of explanations, some of them being a weaker Antarctic surface albedo feedback, ocean heat uptake in the Southern Ocean, Antarctic ozone depletion, and varying Antarctic heights. As you can see in the graph to the left, Antarctic temperatures have much more variability than global temperatures. Knowing that these different latitudinal regions have different warming rates, I created this graph with latitude on the x-axis and warming rates on the y-axis. I obtained the rate of warming at each latitude by performing ordinary least squares linear regression on the average of the anomalies at all the latitudes from years 1975 to 2014. This result is really interesting because it highlights a distinctive positive trend here with a large increase as we go near the Arctic. This trend matches the phenomena I've discussed before concerning the Arctic amplification, as well as the slower warming rate in Antarctica. So knowing the approaching perils of tipping points and also the differing rates in different latitudinal regions of the planet, it's extremely crucial to have an idea of what temperatures will look like in the future, so we'll be better equipped to combat these issues and estimate when tipping points will arrive. So the next step I worked on is projecting future surface temperatures, both globally and regionally. So to project into the future, I turned to CMIP6 models, which are computer and physics-based models of the Earth's climate and include both historical simulations and future projections for many different variables, including the one that I focused on, which is surface temperatures. So two studies, one led by Papalexio and another by Fan, analyzed multiple CMIP6 models and how reliable they are based on comparisons with observational data. So both of these studies found that while most models are able to accurately reproduce historical spatial patterns and trends, there exists a large spread across both different models and different regions. And because there's so much variability between different models and just such a large spread, one of the main tasks for my research project was to identify which models are the most reliable so we can use them to project into the future. So based on previous results from their studies and some analysis of my own, I chose 11 CMIP6 models to analyze from institutions all over the world, including some from the United States, including a model from the Department of Energy, as well as several from places like China and various European countries. So I replicated the latitude-dependent graphs that I showed earlier, but this time with the 11 CMIP6 models. In this figure, the thick red and thick black lines are the observational datasets from GISTEMP and Berkeley Earth, which were compared to each CMIP6 model to determine which models are the most accurate so that we know we can rely on them to make accurate future projections. One major inconsistency between model and observational data is that the warming rates in some of the models begin to drop in the Arctic. However, the two observational datasets show that there should not be a drop in the Arctic, but rather a slow increase and then a straight flat line. So I decided to look more into this issue and focus the graphs onto the Arctic region. Just to reiterate, if you look at the observational datasets, they increase at first and go relatively stable, but a lot of the models show an increase and then a decrease. So to further hone into this issue, I determined the linear trend of each model and observational dataset using ordinary least squares. The table on the left here is organized from the lowest slope to the highest slope. The observational datasets are highlighted in purple as shown here. It's really intriguing to know that all of the models have a lower linear trend than the GISTEMP data, and all except two models have a lower trend than the Berkeley Earth data. One possible cause of this issue, as outlined in a paper by Kos Ravi, is that there are problems in terms of AW layers and the halocline, as well as other forcings in the Arctic Ocean that cause the CMIP6 climate models to develop inaccuracy and a large spread in both the simulated temperature and salinity. Another study done by Tsai found that in the 22 climate models that they evaluated, most of them underestimated mean surface temperatures in the Arctic from 1979 to 2014. And there was also a significant spread in these models, once again reaffirming that there's inaccuracy in the Arctic simulations that led to the inconsistencies with observed data that I mentioned earlier. So due to these inconsistencies, when projecting what temperatures will look like in the future, I only wanted to use the models that have as little inaccuracy as possible. So after using statistical analyses to determine the most accurate models, I only wanted to use the two best models based on these statistical indices to project surface temperatures into the future. And so I selected the top two most reliable models using three metrics: the root mean square error, the mean square error, and the coefficient of determination, which is otherwise known as R squared. And so I ranked the models respective to both the GISTEP and Berkeley Earth observational data. The models were ranked slightly differently in comparison to each of the two observational data sets. As you can see in the slight difference between this graph, which is with respect to the GISTEP data, and this graph, which is with respect to the Berkeley Earth data. However, the top four models and the top two most accurate models remained the same, just in a different order. And I chose the top two models to use for future projections. And the models are from the GIST climate model and the F-GOALS climate model. As you can see here, the Berkeley Earth observational data ranked the GIST model as first, and the GISTEP observational data, as seen here, ranked the F-GOALS climate model as the best model. So these are some of the Taylor diagrams I made to graphically compare the models. Taylor diagrams quantify degrees of correspondence between modeled and observational behavior using three metrics: the Pearson correlation coefficient, the root mean square error, and the standard deviation. So the different models are denoted by the different colored circles here, and models that agree well with historical data are closest to the point marked as reference on the x-axis. In this case, the GISTEP and Berkeley Earth datasets are the reference data, and they're noted by these stars. So as you can see, these Taylor diagrams mirror the previous rankings I showed in the tables. EC Earth 3, denoted by the dark green, is furthest from the reference point, and it's last in the ranking in the tables. And the GIST and F-GOALS models, which are the lighter green and magenta circles, are the closest to the reference point, which makes sense because they were ranked the highest by those statistical metrics. So using F-GOALS and GIST to simulate what the temperatures will look like until the year 2100, you can see that the models predict that the Arctic surface temperatures could reach an astonishing 6 degrees Celsius above pre-industrial levels by the end of this century. To put that into perspective, that is the same temperature difference between the Ice Age and today. Rapid Arctic warming threatens to destabilize weather patterns across the Northern Hemisphere and eventually the entire Earth. It disrupts the polar jet stream, which normally contains cold air within the Arctic Circle. But as the temperature difference with lower latitudes decreases, the jet stream weakens and becomes more erratic, allowing frigid, cold air to plunge southward, causing extreme winter storms while warmer air surges north. And we're already seeing the impacts of this. For example, the polar vortex events of 2019 that brought bitter cold to places like Texas and Florida were caused by a more unstable jet stream pattern linked to Arctic amplification. These weather extremes will only grow more frequent and intense as warming accelerates further, and they may become commonplace once we breach these tipping points. Furthermore, the potential collapse of the West Antarctic ice sheet could trigger 3 meters or more of irreversible global sea level rise caused by the warming temperatures as shown here. Low-lying coastal cities and island nations would be devastated. So these tables show the two climate models' estimations on when global tipping points and regional thresholds in various regions will arrive. They suggest that these tipping points and thresholds are approaching sooner than previous studies anticipated. In fact, all models unanimously agreed that the Arctic had already surpassed the 2.5 degrees Celsius threshold of warming before 2014, and they both estimate that we will reach the global 1.5 degrees tipping point in the next couple of years. The scale of the climate emergency means we now have to seriously consider methods of geoengineering as a last resort to curb warming. Proposed ideas like atmospheric aerosol injection, marine cloud brightening, and space-based mirrors that reflect heat may seem like ideas from science fiction, but climate intervention on this massive scale may soon be our only hope to avoid climate tipping points. As scary as it sounds, we have reached the point where we must research and develop geoengineering capabilities just in case we need to deploy them rapidly. This is how dire the climate prognosis has become. Furthermore, the science connecting human greenhouse gas emissions to climate change is extensive, diverse, and definitive, but misinformation persists, so it's important to understand the evidence. So the greenhouse gas is well-established physics. Carbon dioxide, methane, and other greenhouse gases act as a blanket, trapping more heat. Carbon dioxide levels today are 50% higher than before the Industrial Revolution. This means that more heat is retained, which raises global surface temperatures. So the patterns we expect from physics are happening. Nights are warming faster than days, the troposphere is warming while the stratosphere cools, and the tropopause is rising. The enhanced greenhouse effect emphatically fingerprints human activities. However, there still exist people known as climate change deniers. So they argue that warming is just part of these natural cycles. But multiple lines of evidence disprove this. The pace of change today is orders of magnitude faster than paleoclimatic shifts, and it corresponds precisely with the Industrial Revolution and rising carbon dioxide levels. The only explanation consistent with all evidence is the 50% spike in greenhouse gas emissions from fossil fuel burning and other human-driven activities. So, of course, the fossil fuel industry has long waged a campaign to manufacture doubt and confuse the public, just like tobacco industries denied smoking's harms. But an overwhelming body of evidence implicates greenhouse gas emissions from our cars, farms, planes, and power plants. So in short, the scientific verdict is clear. Climate change from greenhouse gas emissions is established scientific fact through basic physics and multiple lines of evidence. Spreading misinformation about this reality is dangerous. Moving forward, valid debates are about policy solutions, technological advances, adapting to unavoidable impacts, and determining how to redesign economies and societies to be sustainable. Arguing against the reality of human-caused climate change and global warming flies in the face of overwhelming scientific data and serves no purpose other than delaying urgently needed action. So the path forward will not be easy, but we know what needs to be done. It will require transforming our economies, technology, energy systems, agriculture, transportation, and infrastructure, all within a decade. We must rethink and redesign virtually every aspect of our societies to prioritize climate sustainability. This moment calls on each of us to summon the resolve, courage, and creativity to change course and protect our collective future. There will be costs to ambitious climate action, but they pale in comparison to the alternative. We have the knowledge and we have the potential to develop technology to succeed. Now we must find the political and societal will. Fundamentally, we need a societal mind shift away from hyper-individualism, short-term thinking, and gratification delaying. The myth that we must choose between climate action and economic prosperity is false. The opposite is true. Sustainable development is the only viable path. So our generation especially gives me hope. Overall, we understand the urgency and are leading the charge for mitigating climate action. We know the future will be defined by what we do now to stop the planet from unraveling. From school strikes to lawsuits to public protests, our activism is shaking the conscience of nations. The window for action is shrinking, but luckily the pace of renewable energy adoption and sustainable technologies is accelerating. Cities and corporations are stepping up to fill the void left by lackluster national policies. Falling technology costs make decarbonization economically attractive. So in other words, we have the agency in choosing our destiny. It comes down to mustering the courage to transform society amid entrenched interests trying to obstruct progress. We've overcome great challenges before, and we can again if we build determined, diverse coalitions. So yes, actions today won't necessarily bear fruit immediately due to climate inertia, but further delay exponentially increases risks for the most vulnerable. I wanted to bring up the issue of climate justice, which has taken center in many discussions about climate change. So climate justice highlights the fact that while climate change is a global emergency, its impacts are profoundly unjust. It's an existential threat that affects every corner of the planet, but it's also a problem that is deeply intertwined with systematic inequality, affecting different communities in vastly different ways. The most vulnerable and underprivileged populations are the most affected by climate change, but are the least able to adapt to its impacts. Extreme weather events such as hurricanes, floods, and wildfires have disproportionately impacted low-income communities and communities of color. Since 1980, over 95% of deaths caused by natural disasters have occurred in developing countries. Furthermore, the countries and communities least responsible for contributing to global warming will suffer disproportionately in the early stages. The US is responsible for 25% of the world's greenhouse gas emissions, but only represents 4% of the world's population. And overall, the richest 5% of the world's population is responsible for 36% of global carbon emissions, while the poorest 5% is responsible for less than 6%. While the poorest nations and communities are hit first and the hardest by climate change, make no mistake, this crisis will spare no one if it continues unabated. Wealth and power cannot shield any of us from the depleted food systems, displaced populations, damaged infrastructure, spreading disease, degraded air quality, and other sweeping impacts that will be set in motion if we bridge these tipping points. When people are forced to migrate from places rendered uninhabitable, tensions and conflict often follow from the stress on receiving areas. If extreme weather destroys major production regions, supply chain disruptions will send economic ripples and shortages around the world. As health threats like viruses emerge in new areas, all nations remain vulnerable. And if tipping points and if ecosystems collapse past their tipping points, no amount of money or power can recreate lost biodiversity and natural balances that took eons to evolve. Wealth means little on the planet of scarce resources and increasing disasters. Nowhere will be immune from the cascading social, political, and economic crises triggered as the climate destabilizes. While richer nations have an ethical duty to support poorer ones harmed by a problem they did not create, framing climate action as mere charity is misguided. In truth, it serves every nation's self-interest to vigorously rein in emissions and pursue climate justice. No country can isolate or insulate itself from the global interconnected system that climate change disrupts. We will either come together now in our common cause for a livable planet or delay only to our shared peril. This is one crisis that ultimately recognizes no borders or economic barriers. Our fates are bound together in preventing climate catastrophe. True security comes from cooperating for climate stability, not pursuing short-term economic interests. What affects some eventually affects all. No matter our differences, we must unite as one human family to build a sustainable future in which we all have a right to thrive. Our shared destiny hinges on recognizing our common ground. Our window for action is narrowing every day. Yet instead of uniting as one humanity under this shared threat, we've allowed ourselves to be divided by wars, nationalism, and conflict. We must wake up to the scale of the global climate emergency and work together across borders before it's too late. This is the great challenge of our time, and failure is not an option. The very fate of human civilization hangs in the balance. Today, we stand at a pivotal point for our civilization and our planet. Future generations will judge us by the actions we take today. Will we rise to meet this challenge with wisdom, courage, and compassion? I firmly believe we will, because we must. The stakes are simply too high to fail. The climate emergency is daunting, but it is far from hopeless. With a united, resolute effort directed towards a just transition, we can secure a bright future for humanity and the natural world. It comes down to political, economic, and social will. The visions and solutions are clear. What's needed now is activating the social movements needed to demand change. We are awake to the truth and see what needs to be done. A better world is possible only if we break free from business as usual thinking and politics. I ask you to join me in this long but noble struggle. Spread this message, get involved however you can, and never lose hope. Our destiny remains in our hands only if we have the courage to seize it. The road ahead will have obstacles, setbacks, and doubts, but we know the direction in which we must head. Every small step brings us closer to climate stability. Let us walk that path together and write the next chapter in humanity's history, the moment we choose to save ourselves and our planet. The window to secure a livable climate future is closing, but it is not yet shut. We can and we must rise to this challenge. Our destiny is still in our hands. Thank you all for listening.
Okay, thank you very much. I'm very impressed and by our young generations, and we have a good future, and I'm confident, and in the future you are going to and make some changes and face the challenges of the world, and to overcome these challenges. And Jingxing, could you taking care of the question answer period and to see if any question and type in the chat box?
Sure. Right now, I have enabled everyone to unmute yourself, and even you can also open your video. Now, we are open to take questions. So the audience can either ask questions in the chat box or unmute yourself and raise your question.
You can ask any questions to Nicole if you want. Okay, go ahead. Yeah.
Hi, Nicole. Can you talk about what kind of actions you take for to protect the Earth?
So I think protecting the Earth comes down to kind of enabling a wider scale of change, both in terms of social movements and technological advances. So as I mentioned before, there's currently a lot of geoengineering initiatives being developed. And so geoengineering involves creating engineered products to kind of curb global warming. And some examples are machines that can pull carbon dioxide out of the air. And if at some point we're not able to curb our carbon emissions, and the only way to prevent us from reaching these tipping points is to pull carbon out of the air, I believe that to make change in terms of climate change, we should focus on developing these geoengineering capabilities. And then another way of creating change to help stop global warming is kind of political and social advocacy. So for example, this could be advocating to your local politicians to enact policies that, for example, require industries to cut off their carbon emissions at a certain point or to go carbon neutral by a specific date. So I believe that those are the two best pathways we have in order to prevent us from reaching these tipping points.
Thank you. So what kind of actions AEC are doing in this regard?
So I lead a club under AEC called the Eco-Justice Global Alliance, and we're focused on climate justice in underprivileged areas that, as I mentioned before, at the beginning of this crisis, these underprivileged and underserved areas are going to be the most impacted by climate change, and they're also going to be the ones that are least able to adapt or to resist these changes. So we're kind of focusing on youth advocacy and raising awareness of these issues. So we're currently in the process of publishing a book, specifically a children's book, and we're distributing this book to places that are the most impacted by climate change. For example, we've partnered with a Native American reserve to send these books to their local public libraries so that these children can read them and understand kind of how big of an emergency this is, and also empower them to stand up against unfair environmental policies that impact these marginalized communities the most.
Thank you.
Hi, Nicole. I have a question. So my name is Jaden, and then I was curious about your EJGA club. I was wondering if it was like a high school club, and then what you guys do. Like you mentioned talking books, but then beyond that, what else do you guys do?
Yeah, so we're led by a team of high school students. So I'm the co-president as well as another high school senior. And so we're a branch under the All Earth Citizens Foundation. And so we're really focused on climate justice. First is the book that I mentioned. And also we do a lot of political advocacy. So what we do is we'll reach out to our local congressional representatives and also our EPA representatives that specifically focus on environmental justice. And we'll talk to them about implementing environmental policies to fight against climate justice. And so actually next week, we're gonna have a talk with the mayor of Irvine and talk about how we can kind of implement environmental policies and focus on furthering environmental justice in Irvine. So yeah, anyone is welcome to, like any high school student is welcome to join the club.
Thank you.
I think adults in the audience, you can ask question too.
Well, I see a question in the chat box from Prithwis. Besides surface temperature analysis, did the model also reflect the rates of economic developments as one of the input parameters?
So for climate models, there's different social economic pathways called so what we focused on is the socioeconomic pathway 245, which is assuming an economic development in which it's kind of like between the most optimistic estimation for curbing carbon emissions and the most pessimistic. So it kind of is a parameter because we used the socioeconomic pathway that is kind of like the neutral or the average economic development. So there's also different pathways that these climate models have, which is assuming that we could go completely carbon neutral. And in that case, the surface temperatures don't grow as fast. And there's also like the most pessimistic socioeconomic pathway in which the models will estimate that the surface temperatures will go even higher than in the graphs that I showed. So for our analysis, we focused on the average of those two.
Okay, I think if no further questions, and let's thank Nicole one more time. That's all for today, and thank you very much, Nicole. Okay, thank you. Yeah. All right. Okay, so that's all for today, and moving forward, and the CESASC is going to announce other seminars and using our social media. Thank you. Yeah.